The binomial theorem. It's a cool, easy way to expand expressions in the form of a plus b raised to n without opening the brackets up by hand. The theorem looks something like this. And you can see that figuring this out is much easier than expanding a plus b raised to n by hand. But what does the theorem really mean? And why does it work the way it does? Here, instead of offering a formal proof for the binomial theorem, I want to present a geometric visualization that will hopefully give you some intuition for how it works. We start with a pair of axes. Let's say we measure some length, a, along each axis. We can then use these lines to make a square with side length a. The area of the square, the space it occupies, is then a squared. We now increase the length of the sides by b. What is the space occupied by the new square? One algebraic representation of this area is a plus b the whole squared. But another way to represent it is as a polynomial, an expression which only contains terms in the form of a raised to some power times b raised to some power. We can get the polynomial by breaking the square up into pieces and then adding up the space each piece occupies. So, the total space occupied can be represented by the polynomial a squared plus 2ab plus b squared. We could do the same with a cube. We create a cube with volume a cubed and then increase the side length by b. The volume, or the space occupied by the new cube, is a plus b the whole cube. If we break the cube down into pieces, we get a polynomial by looking at how the space occupied by the smaller pieces add up. So, we get this equation. These are the binomial expansions for a plus b the whole squared and a plus b the whole cubed. They're quite neat and relatively easy to visualize. A line for a plus b, a square for a plus b the whole squared, and a cube for a plus b the whole cubed. But what about the expansion for a plus b the whole raised to 4? We'd have to visualize it using the four-dimensional equivalent of a cube, a four-dimensional hypercube or a tesseract. But it's not so easy to visualize and split up a tesseract because we live in a three-dimensional world. And it's even harder to visualize five or six-dimensional spaces, which we would need to visualize these expressions. So let's examine the geometry of 1, 2, and 3 dimensions more deeply and search for patterns there that we can then generalize to higher powers. Our final goal is to answer this question. If you have an n-dimensional hypercube with side length a and you increase the side length by b, how much space does the new, bigger hypercube occupy? Let's start by considering a line segment. It lies on the number line in a one-dimensional space. Its boundaries, its start and end, are zero-dimensional points. A square lies on a plane, a two-dimensional space. To map out points on the square in this space, you'll use two perpendicular axes, one to represent each dimension, the x-axis and the y-axis. The boundary of the square is formed by these one-dimensional lines. It also has zero-dimensional vertices. A cube lies in a three-dimensional space. To map out points in the cube in this space, you'll use three mutually perpendicular axes. The x-axis for the width of the cube, the y-axis for its length, and the z-axis for its height. You can't fully describe a cube in a two-dimensional space with only two axes because you need that extra axis to describe its height. The surface of the cube consists of these two-dimensional faces, one-dimensional edges, and zero-dimensional vertices. So what if I had the four-dimensional equivalent of a cube? Let's call this a four-dimensional hypercube, or a 4-hypercube for short. We can't visualize that completely, but we know how we might be able to construct it. Remember how we constructed the square and the cube? To construct the cube, we created lines on the three axes and then shifted them along the axes like so. We then completed the cube by making faces that were parallel to each other. Based on this pattern, to create a 4-hypercube, we would need four mutually perpendicular axes. Let's call them x, y, z, and w. We would create the hypercube by shifting lines, planes, and cubes on the axes. And based on the pattern we've seen so far, on the surface of the 4-hypercube, we'd have 0, 1, 2, and 3-dimensional parts. In general, if we want to create an n-dimensional hypercube, we need n mutually perpendicular axes to describe the space it sits in. And on the surface of the n hypercube, you would be able to identify lower dimensional parts, right from 0 to n minus 1 dimensions. Just as on a cube, you can identify 0 to 2-dimensional parts. Great! We found some patterns that told us about the surfaces of hypercubes and the space occupied by hypercubes. Now let's go back to 3 dimensions and try to figure out if we can find an answer to our question using the pattern we found. First, let's increase the side length of the cube by b. We could do this by extending the lines in the positive x, y, and z direction. But, for ease of explanation, let's extend the lengths backwards in the negative x, y, and z direction. The space occupied by this cube is still a plus b the whole cubed. We now need to divide our big cube into parts. One way to do this is by slicing along the axes. When we slice up the cube this way, each part is a 3-dimensional cuboid. All these cuboids have to line up perfectly to form the big cube. For this to happen, the parts of the cuboids that are adjacent to the red cube have to have the same side lengths as the red cube. For example, this cuboid is adjacent to this face of the red cube. So its side lengths along the x and y axes have to be a for it to line up perfectly with the cube. But the side length along the z-axis is free to have any length, and the cuboid will still perfectly align with the cube. In our case, we want the side length of our final cube to be a plus b. So, we'll fix the length along the z-axis to b. This cuboid is only adjacent to this edge of the red cube, so its length along the x-axis must be a. But its lengths along the y and z axes can be different. For our purposes, we'll set them to b. So we're essentially setting adjacent side lengths to a and non-adjacent side lengths to b. Notice that the red cube is in the first quadrant and the cuboids are in the second, third, and fourth quadrants. The quadrants only meet around the origin, they don't cross into each other. And the cubes and cuboids stay within their quadrants. Because of this, they can only touch each other at points, edges, or faces that lie adjacent to the origin. Importantly, there has to be a cuboid next to every part of the red cube that's adjacent to the origin. This 0-dimensional point, these 1-dimensional edges, and these 2-dimensional planes. Otherwise, the final cube would be missing a part of its side. We can group the cuboids in terms of the space they occupy, since this is what we're finally interested in examining anyways. To make the grouping easier, let's represent the space occupied by the cuboids algebraically as the product of their side lengths along the axes. The side lengths will be either a or b. So the space occupied will look like some combination of a's and b's. We can now count the number of cuboids that touch origin-adjacent parts of the red cube. The corner of the red cube lies where the axes meet at one 0-dimensional point. The cuboid adjacent to the corner is adjacent to the 0-dimensional origin. All of its side lengths will be equal to b. The red cube has these 3 origin-adjacent edges. They lie on the 3 axes. The space occupied by each of their adjacent cuboids is the product of some combination of A, B, and B. There are 3 origin-adjacent faces of the red cube, and they lie between pairs of axes. The space occupied by each of their adjacent cuboids is the product of some combination of A, and B. Notice what we just did here. We realize that origin-adjacent parts of the cube are directly related to the axes. The cube touches all the axes. The edges of the cube are one-dimensional, and we've placed them on the axes so that each one-dimensional axis can describe an edge completely. The faces of the cube are two-dimensional, which means we must have 2 axes in place to describe them. If we take all possible pairs of axes, we find that all possible origin-adjacent faces of the cube lie between them. This idea is key to generalizing the binomial theorem. Let's say we have a 4 hypercube with its corner aligned to the center of 4 axes and its edges lying along the 4 axes. We can count its origin-adjacent parts based on the axes. Remember, this is not what axes look like in 4 dimensions. We only know that they would meet at an origin, which is why we're representing them like this. The 4 hypercube would have one origin adjacent 0-dimensional corner where the axes meet. It would have 4 one-dimensional edges on the axes. Each pair of axes would have one 2D face between them, and those would be the origin adjacent 2D faces. There are 6 possible pairs of axes, which give us 6 2D faces. And each set of 3 axes would have one origin adjacent 3-dimensional surface between them. There are 4 sets of 3 axes, which gives us 4 3-dimensional surfaces. Each of these origin adjacent parts must have an adjacent 4-dimensional cuboid. The 4-dimensional cuboid that's adjacent to the corner would have all its side lengths equal to b. So it would occupy a space of b times b times b times b. The 4-dimensional cuboids adjacent to the edges would have one of their edge lengths set to a. So these would be the spaces occupied by them. The 4-dimensional cuboids adjacent to the 2D faces would have 2 of their edge lengths set to a. So these would be the spaces occupied by them. And finally, the 4-dimensional cuboids adjacent to the 3D faces would have 3 of their edge lengths set to a. So these would be the spaces occupied by them. The space occupied by the entire enlarged hypercube is the sum of the spaces occupied by these 4-dimensional cuboids plus the space occupied by that original red hypercube. That gives us this equation. And this is exactly what the binomial expansion of a plus b the whole raised to 4 looks like. You can try expanding by hand to confirm this. We've almost come up with a generalized version of the theorem, but there's one thing to figure out before the big win. Is there any easy way to count the number of possible sets of axes? There is, and the answer lies in combinatorics. To calculate the number of possible combinations in which we can choose r axes out of n axes, we can use this formula. So n choose r is n factorial upon n minus r factorial times r factorial. If you need a refresher on how this works, Khan Academy has a great video on it that you can check out. But for now, let's accept that it works and see how we can use it here. We are finally equipped with everything we need to generalize the theorem to n dimensions. In n dimensions, we would have n axes. At the origin of n axes, we would have an n hypercube with a side length of a. To find how many origin adjacent corners, edges, etc. we have, we need to find the number of possible sets of axes from our n axes. How many sets of 0 axes do we have? Well, that's n choose 0. So, the n hypercube would have n choose 0 origin adjacent corners. How many sets of 1 axes do we have? N choose 1. So it would have n choose 1 origin adjacent edges. How many sets of 2 axes do we have? N choose 2. So it would have n choose 2 origin adjacent faces, and so on until we get to n choose n minus 1 origin adjacent surfaces. We would then extend the side lengths of the n hypercube by b. N choose 0 n cuboids would occupy a space of b times b times b, and so on. N choose 1 n cuboids would occupy a space of a times b times b times b times b. N choose 2 n cuboids would occupy a space of a times b, and so forth. We can rewrite this like so. The cuboids are n-dimensional, so the sum of the exponents has to be n. If we tidy this up, we get this expression, and there you have it, the generalized form of the binomial theorem. Remember, we largely based everything here on a pattern, and patterns sometimes break down in math. Formal proofs are important to verify intuition. But isn't it beautiful to step back from formality for a minute and let intuition and imagination have their fun?